Okay, so in order to start the last unit, which is electrochemistry, we need to take a walk down redox memory lane. So we saw this in chapter 4. A reduction-oxidation reaction is one where not only are bonds being broken and new products are formed, but electrons are also transferred from one atom to another during this process. So that's called oxidation and reduction. Redox reactions are short for atoms that are losing electrons are being oxidized, and atoms that are gaining electrons are being reduced. Now, the thing that kids most often get confused is the switching of electrons occurs between the reactants. So this reactant and this reactant will transfers electrons to each other, and you will notice what happened on this side of the reaction. The other thing that you must be very crystal clear about is reaction and oxidation must occur in pairs. You cannot have something gaining electrons without something losing electrons, right? So if when you are doing your calculations, you determine, oh, well, this one's reduced but nothing's oxidized, nope, you've made a mistake. Look again closely. So the standard that AP has set for you is that you should be able to recognize a redox reaction when you see one. So here are some clues that point you towards a redox reaction is happening. So oxidation is a process that occurs when the oxidation number of an element increases. An element loses electrons, it adds oxygen, it loses hydrogen, or a half reaction has electrons as the product. Now the clues that reduction is taking place are exactly the opposite of oxidation. The oxidation number of an element decreases, it gains electrons, it loses oxygen, it gains hydrogen, and the half reaction has the electrons in the reactant side. You were taught that Leo the lion says GR, that is your mnemonic for the loss of electrons is oxidation and gaining of electrons is reduction. This entire unit is taught with mnemonics, and I'm proud to say that almost all of them involve cats. Kind of tricky. All right. So in order for you to judge whether or not electrons have moved from one reactant to another reactant, you have to assign oxidation numbers or an oxidation state to each one of the atoms in a reaction. And this is how you do it. Now, this is a bookkeeping method that really doesn't exist. It's just you being able to visualize what's happening to the electrons. Here are the rules for assigning the oxidation numbers. Atoms in their elemental form have an oxidation number of 0. So copper, in its standard condition, is a solid. And you would know that copper has an oxidation number of 0. Typically, we write the oxidation number up to the right of the atom that it belongs to. However, copper in a compound, an ionic compound, copper 2 chloride, has an oxidation number of +2. One of the things kids mess up with all the time are the diatomic elements, which are Hofbrinkel. They have oxidation numbers of 0 as well. So chlorine, even though it is paired with its twin, still has an oxidation number of 0. Monatomic ions have an oxidation number equal to its charge. What does that mean? That was pretty hilarious. I asked what it means, and 3 people yawned audibly. All right, I know you're tired. Hang in there. All right, potassium oxide. Potassium has a charge based on its oxidation number is based on its charge, which is +1. Why? It's in group 1. It's an alkali metal. It always has a +1 charge. you would write that here. Oxygen is the nonmetal here, it has a -2 charge. Nonmetal have negative oxidation numbers. Oxygen is -2 in all compounds with the exception of the peroxide, in which it's -1. H2O2 is the only peroxide you need to worry about. It's hydrogen peroxide. And oxygen in a peroxide is -1. Now hydrogen, by virtue of the fact of that one valence electron, can do a number of different things. When it's with a nonmetal, it has an oxidation number of +1. When it's in an ionic compound where it is the anion, this is sodium hydride, it will have a -1 charge. When it is in its elemental form, it has a 0 charge. The sum of oxidation numbers in a neutral atom or a neutral compound, this really should be a neutral compound, is 0. You need to take that into account when you're trying to assign oxidation numbers to compounds. And please take out your Redox practice worksheet. Sometimes it's easy to figure out what oxidation numbers are by virtue of the fact that the charges will add up to be 0. And you can just look at them and inspect it. When I look at carbon monoxide, I know that this is not a peroxide, so oxygen must be -2. And I know that whatever carbon is, when added to -2, it gives a total charge of 0. Therefore, that carbon must be +2. Okay, and for the most part, you can do all of these like that. I do want to draw your attention to an old convention that nobody's paying attention to anymore, but it might be confusing to you. It used to be that these two things meant something different. One meant the oxidation number and the other meant the charge. People are just kind of leaving that go. I don't care which way you do it, and neither does AP. They mean the same thing. Right. Sometimes it's kind of tricky to see which atom, the oxidation number of all the atoms. For you, when you can't figure it out just by inspection, I invite you to use the algebra method. And here is the algebra method, and I'll demonstrate it with the potassium dichromate. The first thing you do in the algebra method is you list the atoms that are involved. There is a potassium, a chromium, and an oxygen. Then you count them. In this compound, there are 2 potassium, 2 chromiums, and 7 oxygens. Then you insert the oxidation numbers for the elements that you know. This is an alkali metal. Its oxidation number is the same as its charge, and that would be +1. Oxygen in a non-peroxide is always -2. Chromium is a transition metal. They are famous for being multivalent or having different oxidation numbers, so we don't know what that is yet. But we do know when we add the respective charges up, they will equal 0. And the charge here would be 2 times 1 for +2, 2x, and -14. So we have an 8th grade algebra problem. +2 plus 2x minus 14 is equal to 0. 2x minus 12 is equal to 0. 2x is equal to 12. X is equal to 6. That lets me assign the oxidation numbers to each member of the compound like this. Potassium is +1, chromium is +6, and the oxygen is -2. Please note that you put the oxidation numbers on top to find the total charge of each one of the atoms, you multiply it times the number of atoms. Are we good there? Now, generally, if you have to make a guesstimate and you don't know which one of the atoms changes oxidation number, look for the guy in the middle, the one in the middle, the one in the middle, the one in the middle. And 9 times out of 10, you're correct. But in this particular case, you have a transition metal, which is multivalent, and you have a polyatomic ion. You need to assign oxidation numbers to all of them, and sometimes it's unclear. In this case, there's a giant clue, because this is an ionic compound, a metal and a non-metal. And when they wrote the formula, they took the oxidation numbers and they crisscrossed them. You can uncrisscross them to figure out the oxidation number. Chromium is +3, and the entire sulfate ion is -2. That allows you to figure out what the sulfur is. All right, would you put that away and bring your notes back out? Now, somebody way smarter than me figured out the half reaction method of balancing these equations, and in one step, it balances for mass and it balances for charge. But it requires you to follow the directions exactly as they're written. And the first step in this is to figure out the half reaction. And really what you do is you've assigned oxidation number to all the atoms, then you inspect it and figure out what is the oxidation part and what is the reduction part. The oxidation part has what happening to the oxidation number across the arrow. It does increase. The oxidation number increases across the arrow, so that shows you what the oxidation half reaction should be. And then you find the reduction half reaction as well. And then that brings you to the next page, which are the step-by-step instructions for balancing a redox reaction in an acidic solution. I'm betting strongly that you're not going to have to do one for a basic reaction, so I'm not even going to show it to you. In an acidic solution, these are the steps that you do. Number 1, you assign oxidation states to every atom in the equation. And then you write the oxidation and the reduction half reactions. Once you have written a half reaction, then you balance each half reaction separately, then add them together. To balance a half reaction, first of all, you balance by mass. Anything that's not an H and O, you balance by changing the coefficient. If it is an H or an O, we start with the O first. The only way you can make the oxygens the same on both sides of the arrow is to add a water to the side that has fewer oxygens. When you add water to that side, the opposite side gets unbalanced by hydrogen. The only way you can balance those hydrogen is by adding a proton to that side. Once you have all the mass straightened out, then you look to see how many electrons go from one side to another. And you do a small balance in there that I show you. Once you have both half reactions together, you have to make sure that the number of electrons are the same. Then you add that whole mess up together. Personally, I think this is way easier to show than tell. So let's start. You will notice that this is a net ionic equation. This is a net ionic equation that we are going to balance in an acidic environment. Another way to write this is the permanganate ion, and when it is combined with the sulfite ion, the manganese +2 ion results, and the sulfate ion results. Remember, there are other things that are attached to these ions, other ions as well. They were spectator ions and do not appear in the reaction. Another way to write the permanganate ion is to recall that the entire permanganate ion has a -1 charge. So let's assign some oxidation numbers. Oxygen has a charge of -2, so that means all of the oxygens give a -8 charge. The manganese has to give a plus charge that when it's added to the -8 results in a -1. That number would be 7, +7. The entire sulfide ion has a -2 charge. The oxygen is -2, so that's 3 times -2 is a whole -6 charge that's being given by all the oxygens. The one sulfur has to contribute some number that when you add it to -6 leaves you with a -2, +4. The manganese ions oxidation number and charge are the same. Sulfate would be -2, and the sulfur would be +6. 6 plus -8 results in a -2. Are we clear? Now you need to look at this and determine what has been oxidized. What has been oxidized?
Sulfur.
Yep, sulfur has been oxidized because the oxidation number is increased across the arrow. It has lost electrons. So therefore, the manganese has gained electrons. Its oxidation number decreased. Now you can start with either half reaction that you want. For some reason, I always do the oxidation one, and I'm driving this bus, so that's where we're starting. Now, you do not need to break apart the compound where the atom that is oxidized is found. So we'll take the whole sulfate ion that has a +2 charge, and it goes to the sulfate ion, which has a -2 charge. Now, just for grins, so I keep things straight, I'm going to temporarily write the oxidation number of the sulfur above and I'm writing them temporarily, and I am circling them because they do not belong in the final reaction. I'm just looking at it so I can remind myself what's happening. So my directions say balance by mass first, and we start with something that's not an H or an O. I see one sulfur on each side. It doesn't need to be balanced, does it? Here, I see 3 oxygens on this side and 4 oxygen on that side. That does need to be balanced. And the only way I can balance is by adding a water to the side that is oxygen deficient. That leaves me 4 and 4. I'm good balanced there, but when I added the water, I unbalanced the product side of hydrogen. The only way to fix that is by adding protons, and I have to add 2 of them. Now, I see that the charges are not the same. I need them to be the same. And in order to do that, I need to add electrons to the side that is too high, and that would be this side. And I'm going to add 2 electrons. 2 minus plus 6 will give me +4. That means I'm good to go. I've accounted for the electrons that move. What this is meaning is the sulfur here is different from the sulfur here because the sulfur here lost 2 electrons. Good? That's totally done. I'm ready to move on to the reduction portion. The reduction portion has the permanganate ion going to the manganese ion. Manganese, both one on each side, good to go. I can see that I'm going to have to add 4 waters to this side. So now I have 4 oxygens on each side. I'm going to have to add 8 protons on this side. And then I'm going to have to talk about what happens to the electrons. This side is 7, this side is 2. Therefore, I have to add some electrons. How many and to what side?
5 to
Five
the
on one
reactants.
side.
5 to the reactants. Okay. Now, I've effectively shifted the electrons here correctly. And now I need to look at the electrons between the two half reactions. 2 and 8 and 5 are not the same number. And they have to be the same number because not only am I balancing mass, I'm balancing charge. So I'm going to have to look for the lowest common factor between 2 and 5, which is 10. And I'm going to have to multiply each complete half reaction by that lowest common factor. So this would be a 5, and this would be a 2. It's kind of messy, so I'm going to rewrite it quickly. 5 sulfites plus 5 waters, 5 sulfates, 10 protons, and 10 electrons. And on my reduction, 2 permanganates plus 16 protons plus 10 electrons yields 2 manganese ions and 8 waters. Now I'm ready to add these up, but before I add them up, I can simplify by taking care of anything that is spectating. Because I've done this correctly, the electrons totally cancel out. I look here and I have 5 water on this side and 8 water on this side. These 5 waters will take care of 5 of these waters, leaving me with 3. These 10 protons will take care of 10 of those protons. And I've simplified this as much as I can. So I end up with 5 sulfites and 2 permanganate ions, 6 protons, yielding 5 sulfates, 2 manganese ions, and 3 waters. And that's the completed net ionic equation that's balanced for mass and for charge. And why do you have to do this? Because, well, no, actually not. You need to be able to determine the number of electrons that are exchanged in a redox reaction because we're using this to our advantage. How many people remember physics? Do you remember what a current is?
Yes.
What?
Flow of electrons.
The flow of electrons over the flow of electrons. The charge moving past a point. Yeah. Okay. So we are taking advantage of that moving electrons to make a current. All right, so what's happening here is because of the electrical potential, we're separating this all out, because of the electrical potential, we can make a battery using nothing more than chemicals. Yes? Okay. Now, let's recall how a waterfall works. At the top of the waterfall, there's a high potential energy, and at the bottom of the waterfall, there is a low potential energy. And that water will move from high to a low potential energy, correct? Same thing with the potential of electrons. They flow from high potential energy to low potential energy, and that flow of current, that flow of electron makes a current, and we use it to do useful work, yes? That's how your cell phone works, yes? Okay. All right, so electrons flow through the wire we get a current. But we have to separate the two parts of the reaction in order to get that to flow. Yes?
Like, how'd you know when you were doing the hack reactions to put the electrons, like the oxidation on the right, on the other side? Why didn't you just do like -2 electrons on the reactant side?
Because you can only, in all balancing things, you can only add stuff.
Okay. So it's just, you put them wherever you have to add them.
Wherever you can add them to make,
Yeah, so don't subtract.
now, personally, what I do is when I figure out the oxidation part of the equation right then and there, I know that in oxidation, the electrons always go on the product side. I also, another rule of thumb for me is I always put the electrons on the side that has the higher oxidation number. And then I don't worry about it. It kind of takes care of itself. But the rationale that I explained is the logic that you're supposed to use. Personally, I think it's just rho, and it's a small piece to what we need this to do. Okay. All right, so tomorrow we'll be talking about how to get current to flow and how you will use that current. All right, you may now begin everything else you have to do.
So we're gonna make a battery.
We are